All right, hello everyone, and welcome to lesson 5.1 for the AP Chemistry curriculum, which is on reaction rates. So not all chemical reactions are going to happen at the same speed. Some happen almost instantaneously, while others take minutes, hours, or even longer. In this unit, we're going to focus on reaction rate, which is how fast reactants are turned into products. Our goal is to understand how different experimental conditions like concentration, temperature, surface area, or catalysts affect that speed. Reaction rate is measured as an amount of reactant used up or product formed over time, and the balanced chemical equation helps us see how the amounts of each substance change as that reaction happens. So rate is simply a measure of how something changes over time. In chemistry, that change usually refers to concentration, so reaction rate tells us how fast reactants are being used up or products are being formed. We determine reaction rate by tracking changes in measurable quantities like mass, volume, moles, or molarity as time passes. The unit of time can vary depending on how fast the reaction occurs. Some reactions happen in seconds, while others take much longer. What matters most is the idea of change per unit time, not just the total amount that reacts. When a bubble filled with butane is ignited, like you see my students doing here on the slide, that reaction is going to happen extremely fast. You're going to see a sudden flash of flame, and the reaction is over in about 2 seconds. This tells us that the reaction has a very high reaction rate. So in a short amount of time, a large amount of reactant is converted into product. Reaction rates can be explained by the idea of activation energy, which is the minimum amount of energy required for a reaction to take place. Even if a reaction releases energy overall, like a combustion reaction, for example, the reactants still need a certain amount of energy when they collide in order for a reaction to take place. So energy profile diagrams are great to use because they help us visualize that activation energy in the reaction. So looking at these profile diagrams, we can see on the x-axis we have reaction progress. So as time moves forward, we're going to go to the right on that x-axis. And then on the y-axis, we have our potential energy. So we can see in an exothermic reaction, which means energy is released, of course, our reactants are going to have more energy than our products because we're getting rid of energy. And then in our endothermic reaction, we're going to be absorbing energy. So it makes sense that our products have more potential energy than our reactants. Now let's compare the activation energy for these two reactions. We can see in this exothermic reaction, the amount of energy required for those particles to collide and actually become products is a lot lower than in the endothermic reaction. So we're going to be using these energy profile diagrams throughout Unit 5 to understand reaction rate and be able to compare different factors that affect that rate. Collision theory explains reaction rate by focusing on what is happening when particles interact with one another. For a chemical reaction to occur, those reacting particles must collide with one another, but the reaction rate depends on how often those collisions happen and how many of them are actually successful. So not all collisions are going to lead to a reaction. The particles have to collide with enough energy that overcomes that activation energy and with the correct orientation so bonds can break and new bonds can form. If particles move too slowly or collide in the wrong way, they simply bounce apart with no reaction. And faster reactions occur when there are more frequent and more effective collisions between particles. So let's talk about what we have to do in order to increase rate of reaction. First is increasing reactant concentration. Increasing the concentration is going to put more particles into the same space, which increases your chance of collisions. Next is an increase in temperature. By raising the temperature, you're going to raise the average kinetic energy of those particles, which means they move faster and lead to more energetic collisions that are more likely to overcome that activation energy. Then moving on to increasing the surface area of solids. If you have a solid reactant and you increase the surface area, you are going to expose more particles, which means more collisions can occur. And then finally, adding a catalyst. When you add a catalyst, it's going to speed up the reaction by lowering the activation energy. That is going to allow more collisions to be successful without the catalyst being consumed itself. So let's dive a little deeper into those 4 different factors. First up is concentration. By increasing reactant concentration, it means you're putting more particles in the same amount of space. So you can see in this figure on the bottom here, we have few molecules with few collisions and a low reaction rate. Well, when we increase that concentration, we have many more molecules in the same amount of space, which means they are more likely to collide and have a greater rate of reaction. So when there are more particles present, you have more opportunities for collisions, and more collisions are going to lead to more chances for successful reactions, and that is going to increase your reaction rate. Now, hand in hand with concentration is pressure. So if we are talking about a gas, it's really important that you know it's only for gases. When we increase the pressure, we're going to reduce the volume. And when we reduce the volume, the particles are closer to each other, which results in more frequent collisions, increasing the reaction rate. Next factor is temperature. Increasing temperature increases the average kinetic energy of particles, which means they move faster and collide more often with more energy. However, just keep in mind that all particles are not going to have the same energy. Remember, it's an average kinetic energy. And this is going to be very well described by the Maxwell-Boltzmann distribution you can see in the bottom here. So this distribution shows the spread of particle energies at a given temperature. When a temperature increases, the curve becomes wider and shifts to the right, meaning more particles have higher energies. And as a result, a larger fraction of particles are going to have enough energy to exceed that activation energy, which is shown by this E sub A line here. And because more collisions now have sufficient energy to be successful, the reaction rate is going to increase significantly. For reactions involving solids, surface area plays a major role in reaction rate. So the only particles that are taking part in a reaction are going to be those that are on the surface of a solid. So if you have a large solid chunk, it's going to react a lot slower than something that is broken down into smaller pieces. So when a particle size is decreased, surface area is going to increase, which exposes more particles that can participate in those collisions. And that is going to lead to more frequent effective collisions, which then leads to a faster reaction rate. And that's why powders are going to react a lot faster than large chunks of the same substance. A catalyst increases the rate of a chemical reaction without being consumed in the process, meaning it's not going to be a reactant that then reacts and becomes a product. It goes in and out the same exact way. And it works by providing an alternate reaction pathway that has a lower activation energy than it did before. So as you can see in this energy profile diagram on the right here, the blue route was with no catalyst. And when we introduced the catalyst, all it did was lower the activation energy. So you can see the reactants and the products still had the same amount of energy to start and end with, but the activation energy decreased, which means more particles could reach that amount of energy and allow the reaction to move forward. On a Maxwell-Boltzmann distribution, a catalyst does not change the shape of the curve because the temperature is staying the same. Instead, it's going to lower that activation energy required for the reaction to occur, and that is shown by shifting the activation energy line to the left. When the activation energy is lower, a larger fraction of particles have enough energy to react, and as a result, the shaded area representing successful collisions becomes larger, even though particle speeds have not increased. This explains why catalysts increase rate of reaction without increasing the temperature or being consumed. So let's walk through an example by thinking about the factors that affect reaction rate. The student is measuring how quickly carbon dioxide gas is produced when hydrochloric acid reacts with calcium carbonate. To decide which conditions make the reaction slowest or fastest, we need to look at our surface area, our concentration, and our temperature. So A says which set of conditions will cause the reaction to go the slowest. Well, first let's start out with surface area. If we want a slower reaction rate, we talked about how increasing surface area is going to increase reaction rate. So if we decrease surface area, then we are going to decrease reaction rate. So we are going to want these small chips because those are going to have less surface area than the powdered. Then moving on to concentration, if we want a slower reaction, we want less particles, which means a lower concentration. So that's going to be the 0.005 molar. And then looking at temperature, we know an increase in temperature is going to increase rate. So if we want to have the slowest reaction, we want to decrease temperature, which would be the ice bath. And then B says which set of conditions will cause the reaction to go the fastest. It is the opposite. So we want more surface area, which is powdered, more particles, which is the higher concentration of 0.5, and more average kinetic energy, which is a higher temperature or the warm water bath. All right, so taking that same experiment and looking at a more detailed set of data, we have two different types of chips of calcium carbonate. We have small chips and large chips, and they are dissolved in excess hydrochloric acid, and then the volume of carbon dioxide is collected against time. So we can see here that both reactions are starting at 0 milliliters of carbon dioxide collected, and then both are ending at 80 milliliters of carbon dioxide collected. And we can see from the original information that we have excess HCl, and because the carbon dioxide is coming directly from our calcium carbonate, we know that the same amount of calcium carbonate was used in both experiments because they both created the exact same amount of carbon dioxide gas. The key difference in this graph here is how fast the CO2 was produced. The smaller chips are going to reach that 80 milliliters a lot sooner because they have more surface area, which causes more collisions per second. And that concludes our video on 5.1. If you have any questions, please feel free to reach out. I hope you have a wonderful day and see you next time.